Between when I just start this video and when I'm speaking, just let me know whether you're able to see the video and able to hear my voice, okay? Just let me know by unmuting yourself. So we have only 7 students present here. Okay, so we'll just start. We'll not waste time. It's visible now. So video is quite clear, right? Someone, can you please answer?
Ma'am, it's not visible to me.
Others,
It is not
anyone?
visible.
It's visible? Okay. So I will just start. So today we are going to start with the transfer characteristics of operational amplifier, where we have seen ideal and practical characteristics, right? So we are going to see the transfer characteristics of operational amplifier, that is ideal versus practical. So
Let us see the transfer characteristics of operational amplifier, ideal versus
so
practical.
ideal versus practical we are going to see.
First of all,
We should know why the transfer characteristics are called as transfer characteristics. So these characteristics are known as transfer characteristics because the input differential voltage is being transferred to output as voltage. So for operational amplifier, these characteristics are plotted between difference voltage and the V output. So that is VD and V out.
So let us
see the plots for the operational ideal operational amplifier and practical op amp. So this is ideal op amp and this is practical op amp. Any doubt? Yes, voice
Is your
double
voice
check.
required?
Okay, just a minute. Let me check. I will just connect my mobile and see what's happening. Just give me 2 minutes. I will just check it out.
and these both characteristics are drawn with.
Okay, I got your issue, so I will just solve it out.
Will lead to differential voltage VT and output voltage V naught. And as we can see visually that the difference between both of these is there is a linear region present in the practical operational amplifier characteristics, and in the ideal operational amplifier there is no linear region present. So let us draw these characteristics one by one. First, we are going to see some case.
Hope it is clear now. The voice is clear without any disturbance. Hello. Anyone can just let me know whether the okay.
This is for the drawing the operational amplifier characteristics. This is the symbol of the operational amplifier, and we know that it consists of two input terminals and one output terminal. The negatively marked terminal is called as inverting terminal, and the positively marked terminal is called as non-inverting terminal. And we know that operational amplifier always amplifies the difference of the input signals. Means it amplifies the input differential voltage Vd, which is equal to V2 minus V1. So because the operational amplifier amplifies the difference of input signal, the output voltage is equal to open loop gain AOL multiplied by V2 minus V1, which is equal to AOL into Vd, because Vd is equal to V2 minus V1 here. So we are going to take some cases for drawing the transfer characteristics. First case is if positive voltage V2, this is positive voltage and this is negative voltage. If positive voltage V2 is greater than V1, then what happens to V2 minus V1? It will be equal to positive value. Therefore, Vd becomes positive value. Therefore, V0 is equal to plus AOL into Vd. Second case, if V2 is smaller than V1, means negative input voltage is greater than positive input voltage, then what happens to this Vd? Vd becomes negative, then output voltage is equal to minus AOL into Vd in this case. Third case, if both the input voltages are equal, then V2 is equal to V1, then what happens to Vd? It is equal to V2 minus V1, then Vd is equal to 0. If Vd is equal to 0 and we put the value Vd is equal to 0 here, we get V0 is equal to 0. So first of all, we are going to do ideal operational amplifier characteristics. So for operational amplifier, we know that V0 is equal to gain into differential input voltage Vd, and in ideal case, we have already studied the open loop gain is equal to infinite. So we are going to take the three cases which we have learned just now. So first case is if V2 is greater than V1, then output voltage is equal to plus AOL into Vd. Then if we put AOL is equal to infinity in this place, then we get V0 is equal to plus infinity. And I have already told you in the last classes that when the open loop gain of the operational amplifier is infinite, then the maximum output voltage which we can get from the operational amplifier at the output is equal to the supply voltages, that is plus VCC or minus VCC. So because output voltage should be positive here, then the output voltage at gain is equal to infinity is plus VCC, and the output of the operational amplifier cannot be increased beyond this plus VCC. So it can be taken as saturation value also. Therefore, we can take V0 is equal to plus V saturation also. Second case, if V2 is smaller than V1, then V0 is equal to minus AOL into V, then V0 should be equal to minus infinity. But the maximum value of output voltage should be plus VCC or minus VCC only. Therefore, for negative value of output voltage, the V0 is equal to minus VCC or equal to minus V saturation value. Third case, if V2 is equal to V1, then Vd is equal to 0, then output voltage is equal to 0. Using these values, we plot the ideal characteristics of operational amplifier. So from this equation, we can see that for all the positive values of differential voltage Vd, the output voltage is equal to plus V saturation or plus VCC. And second case is V2 is smaller than V1. So for all the negative values of Vd, the output voltage is equal to minus VCC or minus V saturation. And third case is if V2 is equal to V1, then VD is equal to 0. This is the VD is equal to 0 point. Then if VD is equal to 0, then V0 is equal to 0. So these are the characteristics we can get using these cases. So now we are going to draw the practical operational amplifier transfer characteristics. So again we are going to take this equation V0 is equal to AOL into V2 minus V1 is equal to AOL into VD. Here in practical case, AOL is not equal to infinite. It is very high value, but it is a finite value. Then again we are going to take these cases. If V2 is greater than V1, then V0 is equal to plus AOL into VD. Second case, if V2 is smaller than V1, then V0 is equal to minus AOL into VD. And third case, if V2 is equal to V1, then VD is equal to 0, and therefore output voltage V0 also equal to 0. Now from this equation we are going to find out the differential voltage VD. Then VD, from this equation we can see that if output voltage is equal to AOL into VD, that means because AOL is constant, output voltage is directly proportional to input differential voltage VD. Then if we find from this equation VD value, we get V0 upon AOL, and maximum voltage of the V0 will be plus VCC only. That can be written as plus V saturation. Then VD's maximum value is equal to V saturation upon AOL. So for the linear region, means when V0 is directly proportional to VD, therefore VD will be vary from minus V saturation upon AOL to plus V saturation upon AOL. Then V0 will vary from minus V saturation to plus V saturation in this range. Again, we are going to take some cases. What happens if we increase the VD value beyond plus V saturation upon AOL? As I have told you that the maximum value of the output voltage can be plus VCC or minus VCC only. Then if we increase the value of VD beyond plus V saturation upon AOL, then we get output voltage is equal to plus V saturation only. Then if VD is greater than plus V saturation upon AOL, then V0 is equal to plus V saturation only. And when VD is smaller than minus V saturation upon AOL, means we are increasing the VD value beyond this minus V saturation upon AOL, then we get V0 is equal to minus V saturation only. So let us take one example to draw these characteristics. Here we are taking open loop gain AOL is equal to 10 to the power 4 and VCC is equal to 10 volt. So VD equal to, if we put V0 is equal to VCC here, then we get 1 millivolt after putting these values here. Therefore, VD will vary from minus V saturation upon AOL to plus V saturation upon AOL. From this example, it will vary from minus 1 millivolt to plus 1 millivolt, and V0 will vary from minus V saturation to plus V saturation. Then from this example, it will vary from minus 10 volt to plus 10 volt. So let us draw the table for positive values. For positive values, we are taking VD in millivolt and V0 in volt, because we get VT is equal to 1 millivolt. So we are taking some values 0.2, 0.4, 0.6, 0.8 for VD, and then 1, 2, 3 millivolt for VD. So from 0.2 to 0.8, we are seeing that the output voltage V0 is increasing linearly, and say till 1 millivolt it is increasing linearly. But after 1 millivolt, that is for 2 and 3 millivolt, the output voltage is constant, that is 10 volt. Because if I have told you earlier, if we increase the VD value beyond this plus V saturation upon AOL or minus V saturation upon AOL, we get the same value of the output voltage. That's why we are getting these values. So let us see for the negative values. Here also we can see that from 0.2 minus 0.2 millivolt to minus 1 millivolt, the output voltage is increasing linearly with the input voltage Vd, and after minus 1 millivolt, that is for minus 2 millivolt and minus 3 millivolt, the output voltage is constant, that is equal to 10 volt. So using these both the tables, we can draw these characteristics. So you understood the transfer characteristics. These are the transfer characteristics, and here we can see this region is linear region. In this linear region, the operational amplifier will act as amplifier, and these are the non-linear region. In the non-linear region, the operational amplifier will act as comparator. So let us see the applications of the operational amplifier. Linear region, the operational amplifier is acts as amplifier. So applications are inverting amplifier, non-inverting amplifier, unity gain buffer, which is also called as voltage follower, and next one is voltage to current converter, current to voltage converter. Next is instrumentation amplifier. Next is integrator and differentiator, and last one is summer. For the non-linear applications, we have comparators, schematic trigger circuit, multi-vibrator, precision rectifier, log amplifier, anti-log amplifier, clippers and clampers, and last one is peak detectors. And these all the application we are going to discuss in the next classes.
This is also the part of your syllabus where we are going to consider the linear amplifier with inverting amplifiers, non-inverting amplifiers, buffer, voltage to current converter, current to voltage converter. All these are there in your module as well. Integrator, differentiator, summer, Schmitt trigger, then we do have filters, right? So here only these peak detectors and clipper clampers are not there, log amplifier are not there in your syllabus. But apart from that, mostly your linear and some part of your non-linear characteristics of op-amp has been considered in your syllabus. Okay, so that's all for the characteristics. Hope you all have understood. So we'll move further with the, what to say, configurations which we have studied, right? We have also seen the I guess I did not specified with the configuration, right? We have done only with the modes, single-ended, double-ended, and combined, right? So difference between the inputs that we have just seen the diagrams. So today we are going to see the closed loop configuration as well. So just a minute.
Hello friends, welcome to my channel Learning Electronics. In this video we are
Okay, so we'll just start. So before proceeding to the closed loop configuration, we should know about the feedback. What is feedback? So feedback means in some part of the output, signal is fed back or provided back to the input signal. Then that process is called as feedback. And the operational amplifier that uses the feedback is said to be in the closed loop configuration. Means whenever we see the operation amplifier circuit with feedback, then we can say that the operation amplifier circuit is in closed loop configuration. So there are two types of closed loop configuration feedback, that is negative feedback and positive feedback. So what is negative feedback? If the feedback signal which we are providing from the output is 180-degree out of phase with respect to the input signal, then it is the feedback is called as negative feedback. And negative feedback is used in the amplifier. Another one is the positive feedback. In positive feedback, the feedback is in phase with the input signal and it is used in the oscillator. So let us see the types of feedback one by one more clearly. So the first one is positive feedback. As I have told that feedback signal is in phase with the input signal. So in positive feedback. So because of that, the feedback signal can be voltage or current, which increases the input signal. So because it is increasing the input signal, therefore it is also called as direct or regenerative feedback. And one more disadvantage of positive feedback is that it causes an excessive distortion and instability. Because of that, it is not used in an amplifier. But because the input signal is increasing because of positive feedback, it increases the power of the input signal, and that's why it is used in the oscillator. So next one is negative feedback. It is used in operational amplifiers for amplification. In this type of feedback, the output signal is 180-degree out of phase with respect to the input signal. Here, this circuit is shown of an operational amplifier which is provided by a negative feedback signal. So here the feedback resistor has been used where the output is fed to the input with the help of RF resistor. So RF resistor has been shown. So why it is providing a negative feedback? So if ever any resistor has been connected to the negative terminal of an op-amp, so that is the reason why it is called as negative feedback. So this RF is providing negative feedback to the operational amplifier since it is connected to the inverting terminal of an output. And that is the reason why the output will be 180-degree out of phase. So there is the one question, why we use negative feedback in operational amplifier. As it has been said, the positive feedback increases the input signal. Similarly, negative feedback weakens the input signal. And therefore, it is also called as inverse or degenerative feedback. But in the operational amplifier, we need to control and stabilize the gain, as well as we want to increase the bandwidth of the amplifier. So this negative feedback, when we are providing in the operational amplifier, even though it reduces the amplifier gain, but it controls and stabilizes the gain, and we use this negative feedback. And it also increases the bandwidth of amplifier. This is the reason why negative feedback is used in operational amplifier. So let's see more features of negative feedback. First one, as it reduces the stabilizes the gain. Second, it increases the bandwidth. Third, it reduces the nonlinear distortion. Fourth, it increases the input resistance. Fifth, it also decreases the output resistance. It improves the frequency response. It reduces the noise. And eighth one is it reduces the effect of variation in temperature and supply voltage on the output of operational amplifier. Next one is types of negative feedback. So there are four types of negative feedback. First one is voltage series feedback. Second one is voltage shunt feedback. Third one is current shunt feedback and current series feedback. I guess this all types of negative feedbacks you must have seen in your EDC subject when you have studied. Feedback amplifier was there in your EDC? Regular students, can you please let me know?
Yes, ma'am.
Yes, so these all topics are just an overview. We will not go into the detail of this feedback amplifiers, but there you have seen these concepts using transistors. Here we are just having it using an op-amp. So we'll just give you an overview because the main concepts are clear, which has been done in your EDC subject. Okay, so these are the types of negative feedback. So in the operational amplifier, when we use non-inverting and inverting operational amplifier, we use voltage series and voltage shunt feedback. So we are going to see this voltage series and voltage shunt. So this is the block diagram of voltage series feedback amplifier. So in this we have an operational amplifier block and one feedback network block. So as you can see, this open loop gain, which is equal to V out by V input, and feedback gain is given by Vf, which is beta, that is equal to VAF feedback voltage by output voltage V out. In the voltage series feedback, we have voltage sampling plus series mixing. What is voltage sampling? Whenever the some output part has been given feedback through the feedback network, that is what called as voltage sampling. And what is series mixing? The output of the feedback network when it is provided in series with the input to the op-amp block, that is called as series mixing. So this is next is voltage shunt feedback amplifier. Again in this we have two blocks, op-amp and feedback network. So we use here voltage sampling plus shunt mixing. So as we have seen, what is voltage sampling? That some part of the output voltage is provided to the feedback network input, and that is the reason why it is called as voltage sampling. And what is shunt mixing? The output of the feedback network is given in shunt to the, that means in parallel to the input signal with the current source. So here we have current source. In previously series we had a voltage source. So that is the reason why it is named as voltage shunt feedback. So we'll see the types of configuration that we are going to study in the next session. The first type under the closed loop configuration we are going to study is inverting amplifier, which is a voltage shunt feedback amplifier, and second one is non-inverting operational amplifier, which is voltage series feedback amplifier, and third one is buffer amplifier, which is also called as unity gain buffer or voltage follower. So I hope this is clear. So now we are going to study further part of the closed loop, so that you will understand it very properly. I'm using these videos, online videos, so that you will picturize the things, whatever has been said by me, because when I just go on saying we're using the slides, it is not moving, so you won't be able to understand. So hope this concept, what I'm going to use is going to help you more. Okay, so this is what we have studied about the transfer characteristics today, as well as we have seen the closed loop configuration, which is voltage series and voltage shunt. So we just need to know the basic concept of virtual short circuit. So we'll just play that as well. So we'll just see the virtual short circuit and virtual ground concept of operational amplifier. So let us start this. So first of all, we should know why we use the virtual ground or the virtual short circuit concept. So these concepts are used to determine the closed loop gain and output voltage in the operational amplifier circuit. So what is closed loop gain? It is called as gain with feedback. So that means whenever we are connecting the input and output of the operational amplifier, then the operational amplifier is called as closed loop gain, or you can call it as closed loop configuration. So these concepts are exclusively for amplifiers only. The first one is virtual short circuit concept. It follows two statements. First is according to the virtual short concept, the potential difference between the two input terminals of the operational amplifier is almost equal to zero. That means if we are taking the voltage at inverting terminal and the voltage at non-inverting terminal is with respect to this, then we have V2 minus V1 as the VD voltage. So according to virtual short circuit, that means V2 minus V1 should be equal to 0. Virtually, if it is virtually short, then V2 minus V1 should be equal to 0. And if V2 minus V1 is 0, that means both the input terminals are approximately at the same potential. That is V1 is equal to V2 is equal to 0. So let us prove this two statements. So here we have taken one operational amplifier circuit in a closed loop configuration, and in this we have taken input resistance as Rin, and the drop across the Rin is taken as Vd, that is differential voltage. So voltage at non-inverting terminal is equal to the voltage at inverting terminal, and non-inverting terminal are same. So when we have seen the transfer characteristics, so it has been stated the ideal operational amplifier has input resistance infinite. So if this input resistance is infinite, then it will act as an open circuit. That means no current will flow in this resistor. Because in open circuit, no current can flow. So if we are taking the current at this inverting terminal as IB1 and current at in non-inverting as IB2, then because Rin is infinite, IB1 will be equal to IB2, that is equal to 0. And if we take the current through Rin is equal to In, then In is equal to 0. So now what will be the drop across the input resistance? That is equal to 0. So the formula is written as Vd is equal to In into Rin, because Vd is the drop across the input resistance Rin. So if we put these values in this In and Rin, then we get 0 into infinite, that is equal to 0. So we get the differential voltage Vd is equal to 0. So another formula for differential amplifier voltage is V2 minus V1. And if we put this value 0 here, then we get V2 minus V1 is equal to 0. So from this equation, we have proved the first statement. That means the potential difference between the two terminals of the operational amplifier is equal to 0. And if V2 minus V1 is equal to 0, then V1 is equal to V2 is equal to 0, which states the second statement has been proved. True. So, both the terminals V1 and V2 are same. So, since V1 is equal to V2 is equal to 0, thus the potential at point 1 and potential at point 2 are equal. So, this is called as virtual short circuit concept. That means since this point is at same potential to this point, that means inverting and non-inverting terminal are same and they are virtually short circuit. That's why it is called as virtual short circuit. So let us see this with one example. Here we have taken open loop gain as 2 into 10 raised to power 5, which is the open loop gain, maximum open loop gain for IC 741, and VCC as
मैम
1 volt.
स्क्रीन नहीं दिख रहा है.
एक मिनट क्या हुआ डियर?
स्क्रीन नहीं दिख रहा है आप जो बता रहे हैं.
ओके, स्टार्टिंग से ही नहीं दिखा?
नहीं, अभी जब भी स्टार्ट किए ना तब से नहीं दिख रहा है.
मैंने प्रेजेंट नहीं किया है क्या? एक मिनट, आई विल जस्ट स्टार्ट इट अगेन. ओके, जस्ट अ मिनट, मैंने प्रेजेंट नहीं किया शायद. दिस इज व्हाट हैपेंस व्हेन वी आर यूजिंग मल्टीपल स्क्रीन्स. So sorry, just a minute. I will just present. Okay, I will just repeat. I hope whatever I said was clear. So I will just repeat it once. Hope it is visible now. Okay,
Yes, miss.
screen is visible now. Yeah. So see, this is what where this is. I stated why we need to use the virtual ground concept. So this concept, as I stated, are used to determine the closed loop gain. And what is closed loop gain? That also I stated that when we are giving some part of the output to the input, that is what called forming a closed loop. That's why it has been named as closed loop gain, or we normally call it as closed loop configuration. So when we are giving some part of the output to the input, that is what called as closed loop gain. So these concepts are exclusively for the amplifier. So what is the concept is virtual short circuit. So there are some two statements. First is, according to this concept, the potential difference between the two input terminals of the op-amp is almost equal to zero. So that means if we are taking the voltage at inverting terminal as V1 and voltage at non-inverting terminal as V2, the potential difference between these two should be V2 minus V1. So according to virtual short circuit concept, the potential difference minus V2, that is V2 minus V1 should be equal to 0. So this is what V2 minus V1 is equal to 0 is the first statement. And second says if V2 minus V1 is equal to 0, that means both the terminals are at the same potential. Therefore, V1 is equal to V2 is equal to 0. So we need to just prove this two statement. So we have proved using one circuit. So this was a circuit which was shown where we have connected virtually there we have considered as Rin resistor, and the drop across this Rin is VD, that is differential voltage. The voltage at non-inverting terminal is V1 and inverting terminal is V1, right? V1 at inverting and V2 at non-inverting terminal. So in the characteristics we have seen the ideal operational amplifier has input resistance as infinite. So this means if resistance is infinite, then it will act as an open circuit. That means no current will flow in this resistor. So if we consider the current at inverting terminal as IB1 and at non-inverting terminal as IB2, so we'll state that two currents will be equal to 0. Why? Because since Rin is infinite, and when Rin is infinite, that means it is acting as an open circuit. So when it acts as open circuit, there will be no current which is going to take place. And if we consider the current through this resistance is I in, then that I in is equal to 0. So now what will be the drop across the resistance Rin? So the formula we can use is VD is equal to V is equal to IR, right? So since it is VD which is across Rin taking place, so we write it as In into Rin. And we have stated what is Rin and In. So when you substitute this, we get VD is equal to 0. So why 0 into infinity is 0? Because anything which is multiplied by infinite is always 0. So anything multiplied with 0 is 0, right? So we can also calculate VD as V2 minus V1. So we can directly state VD that is equal to V2 minus V1 is equal to 0. So this is what we have proved the first statement of virtual short circuit. So we state from this, if V2 minus V1 is 0, that means the voltage at both the terminals of operational amplifiers are at the same potential. So we state V1 is equal to V2. So V1 minus V1 is equal to V2 is equal to 0. So if this is the case, when V1 is equal to V2 is equal to 0, we say the potential voltage at V1 and at port 1 and port 2 or inverting and non-inverting terminal is same. So this is what the virtual short circuit concept, because this point is at the same potential as this point. So they are virtually short circuited, not actually short circuited. They are virtually short circuited. Okay. So we'll just see this with one example. So open loop gain, we have considered open loop gain. So we have seen in the characteristics, the maximum open loop gain is 2 into 10 raised to 5. And VCC is equal to 1 volt, we have assumed. So operational amplifier amplifies the difference between the input signal. So output voltage is equal to gain, open loop gain AOL into V2 minus V1. That is equal to AOL into VD. So from this we can find out VD, that is V0 by AOL. So we know the AOL value and VCC, that is output voltage. So we get 5 microvolt as differential voltage, which is very small. So since VD is very small, so it will be approximately 0. So VD, we know it is equal to V2 minus V1, that is differential voltage. So V2 minus V1 is equal to 0 and V1 is equal to V2, that is equal to 0. So hence we have proved this second statement using an example. So the virtual short circuit concept. This is what the virtual short circuit concept. Next one is virtual ground concept. So it is using virtual short circuit concept only. So if non-inverting terminal is grounded, then by virtual short circuit concept, the inverting terminal of op-amp is also at ground potential. So what is virtual short circuit? As stated, that both the terminals of the operational amplifier are at same potential. So if one terminal is grounded, the other terminal will also be grounded virtually. So not actually, but virtually. So similarly, if inverting terminal is grounded, then by virtual short circuit concept, the non-inverting terminal of op-amp is also at ground potential. So here we are going to take operational amplifier circuit. So here we have grounded the non-inverting terminal. So inverting terminal will also be grounded virtually. So if V2 is grounded, then V1 is grounded virtually. Okay, so hope you have understood this topic. So this is what about virtual ground concept and virtual short circuit concept. This is very important concept when we are using operational amplifier. So I guess that's all for today. And next lecture we will proceed further with open loop configuration. Or else how much? What's the time? 9:52. Okay, let me see. Hope, is there any doubt for today's lecture? Thank you that you stated in between that your slides were not visible. Yes, dear anyone? समझ में आया है कि नहीं आया है? Hello. नहीं आया नयन, नहीं समझ में आया, क्या नहीं समझा? Which video you were not able to understand? Just let me know. Hello. Hello. Are you able to hear me? Kritika, what happened here?
Yes, miss. आपकी आवाज आ रही है.
Okay. So no miss means what you are stating? Ki you are not able to understand? No doubts. Okay. I thought you did not understand the concept. Yes,
No,
Nayan?
miss, I had said no to your first question. Miss, I had said no to your first question when you ask, do you have any doubts?
Okay. Okay. So we'll proceed with the open loop configuration so that we will complete that part, and then open loop और ये दोनों खत्म हो जाएगा हम लोग का. I will just open that where it is. प्रेजेंटेशन नहीं हुआ तो बताना. Okay, it will take time, I guess. So we have only 5 minutes, so we'll just take your attendance.
Roll number 1. Roll number 1, 2,
Present, ma'am.
3,
Present, ma'am.
4, Omkar, 5,
Present, Miss.
6, Abhishek is present, 7 is present, right?
Present, Miss. 7.
8, 8,
Present, miss. Present, miss.
9, Aman, 10, Shubham,
Present.
11, Pranay,
Present, miss.
12, Purti, 13, Akshay, 14, Brunali,
Present, Miss.
15, Sanjay, Kritika,
Present, Miss.
16, Harsh, 17, Abdul, 18, Sachin,
Present, miss.
19, Nayan, 20, Aniket,
Hello, Miss.
Aniket,
I had got disconnected. Can you please mark my attendance as well?
yes, Aniket, not there. 21, Megha,
Hello.
yes, Nayan, you're present, I know.
Thank you, Miss.
22, Onkar, 23, Vishal, 24, Deepak,
Present, Miss.
25, Nikita,
Present, ma'am.
26, Sainath.
Present, miss.
Okay. Between yesterday, there was an instruction that diploma students are supposed to come to college to fill up the university admission form. So see that you are going to come today to college, okay? And if not possible, then contact exam cell or I don't know what to say, HOD madam. Okay. And one more thing, Kritika is asking to share the notes. Once I complete one particular module, then what obviously I will share you the notes or whatever video links I have that I'm going to share you in the Google Drive, Google Classroom. Okay.
Okay, Miss.
Okay. Thank you so much. You all can leave.